Hello, today is Wednesday, November 14th, 2018. Welcome to the NERI SimCenter's Advances in Computational Modeling and Simulation webinar series. This is a platform for sharing state-of-the-art practices and advancements in natural hazards engineering. We're joined today by Artie Rogers, a seismologist from the Lawrence Livermore National Lab. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Computational Modeling and Simulation Center, which is easily abbreviated as NERI SimCenter. For more information, visit our website at simcenter.designsafe-ci.org, where you can find links to our research tools, educational apps, workshops, and webinars like this one. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Dr. Rogers is on the technical staff at the Lawrence Livermore National Lab and also holds visiting appointments at UC Berkeley's Seismological Laboratory and the Lawrence Berkeley National Lab. Artie's presentation is titled High Performance Computing, Ground Motion Simulations of Large Hayward Fault Earthquakes. Dr. Rogers and his colleagues generously shared these research outcomes with the SimCenter, which was the basis for our test bed, demonstrating our regional earthquake workflow in the San Francisco Bay Area. The SimCenter is grateful to Dr. Rogers and his colleagues for sharing their work and hope it inspires others to contribute, adapt, and improve the understanding of risk our communities face in natural hazards. Our software is community-driven, so contributions such as this are vital to improving our capabilities, and we hope that it inspires you to also contribute. With that, Dr. Rogers, I invite you to begin.
All right, thanks a lot, Matt. So first, you might wonder why someone from Lawrence Livermore Lab is working on earthquakes. Of course, Livermore and its fellow lab, Los Alamos, are nuclear weapons labs. But most of what we know about foreign nuclear testing, at least right away, is from seismology. So Livermore and Los Alamos have had seismology programs since they were founded. So our group does a lot of national security geophysics, obviously. But another aspect of the lab is under the stockpile stewardship programs to try, in the absence of nuclear testing, numerical simulation of the performance of weapons has been a big part of work at the national labs. So we have a real ecosystem of high performance computing and simulation science. So I'm fortunate to work in that environment. And we're also interested at seismic hazard at the DOE facilities. The DOE has several national labs, including in Berkeley and Livermore and Los Alamos and throughout the nation. And they're exposed to some more, some less, to seismic hazard. So our projects, and particularly Dave McCallan, who's the PI of one of the projects I'll talk about, has been interested in trying to apply these modern state-of-the-art simulation tools to the seismic hazard. So the current project I'll talk about is really part of an exascale computing project. The DOE is trying to get ready for the next generation of supercomputers and to gear up both the codes and the hardware as well as the applications. And this is an application project where we're trying to compute ground motions in fully three-dimensional realistic Earth models using realistic rupture models to calculate motions and then do the engineering piece as well. And so sort of a summary of what I'll talk about is high performance ground motion simulations. I'll be focusing on the Hayward Fault, very close to home here in the East Bay. And we use a code called SW4, which was developed at Lawrence Livermore Lab. And we're doing fully physics, what we'll call physics-based wave propagation. These are not dynamic ruptures, but kinematic rupture models where we specify the choreography of the Earth rupture. We specify the full three-dimensional geologic and seismic properties of the Earth, And we've been focusing on this domain here, which is 120 by 80 kilometers and 30 kilometers deep. And we include the surface topography, which a lot of codes have not included, but it becomes an important factor when you go up to higher frequencies, when the wavelengths of the waves start to become comparable to the size of the hills and mountains. We also include anelastic attenuation. We're trying to get broadband motions and go to higher frequency to capture the frequencies of interest to engineers in the community that Pierre and the SimCenter are working with. So our methods can calculate the static displacements or the offsets that result from, from an earthquake, a dislocation within the earth. The challenge is going up to higher and higher frequencies. And I'll talk about fmax, that's the maximum frequency that we can resolve. And we started off doing this a couple of years ago, getting 2.5 hertz. We've now gone up to 6.9 hertz. And I'll talk about Hmin, which is the minimum grid spacing of our models. That really controls how high a frequency we can resolve. And we've gone down now to 9-meter resolutions. And in order to fit such a big problem into a computer, we need to use high performance computing. Just the size of the memory, we're using tens of billions of grid points, sometimes 100 billion grid points. And, each grid point requires, 500 bytes of memory, just to account for all the material properties and just in the static memory. So we have to do these calculations on high performance computing. We'll show that the motions agree well with ground motion models and that they're relevant for engineering analysis. And sort of the what for or so what about this is, these simulations allow us to evaluate path and site effects as well, and source effects for that matter too. But ultimately, simulations can help reduce uncertainties in seismic estimates, seismic hazard estimates, because path and site effects are repeatable. If we can predict them, then we can use that knowledge and account for it in ground motion models. And then we're still stuck with the aleatory, randomness of the earthquake source. But if we can reduce predictable path and site effects, we can ultimately reduce uncertainties. So the motions that we're calculating, we'll output the motions from a simulation like this shown on the left. Here's the time, the velocity time histories, 3 components. They're used in 2 flows for one for building response. Dave McCallum's written a code called Nevada, which is a fiber nonlinear steel frame building model. He can compute the motions and track the nonlinearities with implicit time stepping and track the interstory drifts and thus the damage to structures. And Boris Yeremich at UC Davis is working on his earthquake soil structure interaction code, which is a domain reduction method where we would then output motions on a dense grid around a soil island that contains the structure. So those are the applications. And of course, it's important to go up to higher frequencies. We want to capture the low order modes, the couple of first, say, 3 modes of buildings. And if we're getting to 3-story buildings, that's getting up into 5 hertz or more. And then for, structures, we want to be able to, like nuclear power plants, are very stiff, and we want to get up to high frequencies approaching 10 hertz or higher. So there's a big push to try to go to higher and higher frequencies in all this work. But this is, of course, a team effort. Really key to this is Anders Peterson and Bjorn Sjogren at Livermore, who developed the SW4 code that I use to calculate these motions. And then I work with Arvin Pitarka and Rob Graves, who are seismologists. Arvin's my office neighbor at Livermore and a source earthquake ground strong motion seismologist. On the engineering team, Dave is the PI of this effort and also heads the engineering effort. Norm Abrahamson has been a valuable advisor on a lot of what we're doing and is helping to guide us as to how simulations might become accepted in the future. And none of this work would be possible without the work at the supercomputing centers we work at, namely the NERSC facility at Lawrence Berkeley Lab and at Livermore Computing at Livermore. So in 1868, there was a magnitude 6.5 to 7 earthquake in the East Bay on the Hayward Fault. It caused great damage, but only about 3,000 people lived in the East Bay at the time. The city of San Leandro and on Hayward were very strongly affected. If you haven't read it, I'd urge you to read the Lawson report. There's a section in the Lawson report following the 1906 earthquake that talks about the 1868 earthquake and the consequences and some of the reports of structural damage. It was quite devastating. This shake map was created by Jack Boatwright and co-workers at the USGS. Zooming in sort of to the area, of course, we're up in Richmond here, but this is looking at the East Bay with the historic, or sort of the Oakland, Berkeley, Oakland, San Leandro area, Alameda, with the historic coastline, and then the felt reports are each of these diamonds, and the Mercalli intensities are up to 7, 8, or 9, and they're really strong here in San Leandro, and that's where the Alameda courthouse was destroyed, and there was real devastation. So this area is capable of very strong earthquakes. Of course, this was 150 years ago, almost to the month, and the repeat time of, there's evidence of 12 events on the Hayward Fault, with a repeat time of about 130 to 160 years. So we're sort of right there in the overtime when we might expect another event here. So as many of us here know, we can't unknow what we know about what earthquakes are capable of. So it's very sobering to think of this historic evidence here in the context of a future earthquake. But that's what we're trying to do. We're trying to calculate the motions for what a future earthquake on the Hayward Fault might look like. Okay, simulations of near fault motions is really, it's needed because that's where the motions are the strongest, but it's also, we suffer from the paucity, from the very few near source recordings of large earthquakes. And the data are highly variable. And you know, as Pierre has collected data for the NGA West, this is one example from Grazier and Kalkin, but you can see as a function of magnitude and distance here, there are very few observations of very large earthquakes greater than magnitude 7 at close range. And there's a lot of variability too, and that's due then, to the vagaries of the earthquake rupture. You know, an earthquake, a large earthquake can rupture up to 50 or 100 kilometers. There's a very strongly heterogeneous slip distribution along that fault. So if you're close to one of those large slip patches, you might experience much higher ground motions than if you're far away from one. If it's rupturing towards you, you'll experience higher motion than if it's rupturing away from you. So all these variations in slip, directivity, rise time, rupture speed are all very important in controlling and shaping the variability that we observe in the limited ground motions we have. Of course, there's the displacement step and the velocity pulse. If you're close to an earthquake, can be a very large pulse that comes by, and some so-called fling step. That's very important in controlling damage to structures. And if you're near a sedimentary basin, all the motions can couple into the sedimentary basin. So they're highly dependent on the specific geometry of the fault, including the fault dip and any bends in the fault, as well as proximity to variations in structure, most importantly sedimentary basins. Here's just a set. These are all, you know, all these motions are from the same earthquake, from the same rupture, but at the same joiner distance, right, which is one of the two really important parameters that enter into GMPEs, distance and magnitude. But you can see there's a lot of variability, and here probably the rupture is going away from this point, and there's a big velocity pulse here, and here's further along the fault, but you know, you can see some very large pulses due to different asperities going off. And of course, we're really important, sometimes we have to be on the fault. We have critical facilities and transportation and lifeline infrastructure that crosses faults, so we have to be able to characterize the near fault motions. And here are just a few examples of such sort of critical facilities. So, but numerical simulations are challenging, and there are three challenges that I'll talk about. There's the mathematical challenge. We must have a method that is accurate and stable and efficient. We want to be able to integrate for long times with very fine time step, and we need a stable method that is accurate in time, that doesn't have growing errors. We've solved that in a way, or really Anders and Bjorn have solved that by using the summation by parts method, which is a provably stable method for solving second order finite difference approximations. And it's They use a higher order, so it's fourth order in time, fourth order in space. It uses mesh refinement, which is important for, which I'll talk about in a moment, but important for memory efficiency. And the code is verified by comparison with analytic and manufactured solutions, including 3D structure. Computational challenges, right? Just to be able to run these calculations, we need access to, we need to be able to run them on billions of grid points to resolve, very fine discretizations from, say, 1 to 10 meters or 1 to 15 meters over large domains. Magnitude 7 rupture could be 70 kilometers. So we need a domain that encapsulates that. And our solution here is just to use more and more powerful computers, but also optimize methods for the specific hardwares. And we have sort of 2 examples of that, most recently being able to run on GPU computers. Really the most challenging obstacles we have to overcome are physical. And one has to do with the source and the other has to do with the Earth model. So for the source, we need a realistic, rupture model. And we use these physics-based models that were developed as part of the broadband platform project with SCEC. Rob Graves and Arvind Pitarka have been working for years in their rupture generation code, and we use the Graves and Pitarka method. But what we really want to be able to do is sample a range of ruptures so we can capture a whole suite of possible ruptures, so we can capture some of that aleatory uncertainty, some of what might be unknowable factors, such as where is the rupture going to start, what is the distribution of slip along the fault. And we have to validate now, in the absence of a magnitude 7 earthquake on the Hayward Fault, which we don't have recordings for, we have to compare against the ground motion, the measured ground motion intensities against the ground motion prediction equations or ground motion models. And we've done that, and I'll show results from that with the NGA West 2. So that leaves us with the accuracy of the 3D Earth model. And we have a model of the geology and the seismic velocity or seismic properties of the Bay Area that we use from the USGS. We know where the basin's edges are at the surface. We've mapped, the geology is very mapped in great detail at the surface. We know the topography, but as we go into the Earth, our knowledge of the structure becomes a limiting factor. And we're hoping to try to improve this through data inversion and by looking at moderate earthquakes. I won't really be able to touch on this too much, but it's a theme and a limitation that we have to be cognizant of. And of course, to validate the 3D model, we want to compare the limited observed data we have for moderate earthquakes against the predictions of the model. All right, so the recipe here to put this all together to compute compute ground motions and 3D Earth models with purely deterministic methods and high performance computing. So we specify the rupture according to Graves and Pitarka. We put in the variations of the material properties as specified by the USGS model here on the lower left. Now I say purely deterministic in that this is not a hybrid approach. We are not using the stochastic method. We are not using random number time series to extend the frequency content. This is all purely deterministic. So the rupture is specified according to the slip distribution shown here in this slip model up in the upper left. Wave propagation according to F equals ma for a solid here, according to the USGS model. And then that's all solved in SW4 using high performance computing. And where it's our goal really to try to drive this to higher and higher frequencies and also shorter runtime so we can enable sampling of the rupture and Earth model. All right, SW4 is a fourth order summation by parts finite difference code developed at Livermore. It's a node-centered, it solves a second order accurate equations, and it has very efficient supergrid boundary conditions that extinguish the waves that are propagating out to the edges. It has mesh refinement, so commonly, and it handles topography. So for topography, it stretches the mesh in the vertical direction to be able to conform to the topography. And then we can have mesh refinement in depth, where we double the mesh size or grid spacing as we go from the surface to depth. And that's important because the seismic wave speed increases with depth. So we don't need to oversample. If we had a fixed grid, we would oversample the wave field here with too many, we'd essentially be wasting memory down here. So this allows us to really efficiently use the memory. And what ends up happening is most of our grid points are like 90% are concentrated near the surface. The code is fourth order in time and space. It counts for fully 3D material properties, including anisotropy. I talked about mesh refinement. And then so lately under this exascale computing project, a lot of emphasis has been on optimizing the code for specific hardware. And specifically, we've been running on the Cori Phase 2 machine run at NERSC at Lawrence Berkeley Lab. And that machine has 68 cores per node. So it has fast memory within the node, and we want to take advantage of that. And before we were using MPI, which is a more expensive memory exchange method. But within the node, you can use OpenMP or multi-threaded code so that you can essentially share memory and have very efficient messages within the node, between cores on the node. But when you go from one node to another, you still have to use MPI. And Anders and Bjorn worked that out to be able to make that optimized and for Cori. And then separately at Livermore, there's been an effort to get ready for the next generation of supercomputers, which will be based on GPUs or graphics processing units. And I'll talk about that in a bit here. So in June of this year, we got access to almost all of Cori for 24 hours or so, and we ran a large simulation that resolved ground motions in this region here, this 120 by 80 kilometer domain for a magnitude 7 earthquake on the Hayward Fault that follows this solid line here at the surface. Be it it's a bilateral rupture, so it starts in San Leandro and propagates in either direction. And we resolved that to 5 hertz. And so to do that, we had a 12.5 meter grid spacing. And that used over 500,000 cores and ran in 10 hours. And at the time, it was the highest resolution deterministic 3D simulation for the Bay Area. I'll talk about some of those motions a little bit later. But meanwhile, at Livermore, there was an effort to port SW4 to GPU architecture under a separate effort that took 3 years to do and explored lots of different possibilities. But about August or so, it became possible to run that code on the Sierra machine, which is a new machine, relatively new machine at Livermore. It's just was announced. It's now number 2 on the top 500. And in August, we ran the same calculation that we did on Cori. So here on the left are the sort of statistics for running on Cori. We used 85% of the machine on 500,000 cores. And but with Sierra using the GPU, and of course the GPU, a GPU card has 4,000 cores on it itself. And each node of Sierra has 4 GPU cards. So you can have a credible amount of memory on a single node. So we ran the same calculation, but only using 6% of the Sierra machine on 256 nodes and about the same runtime. And it's essentially was 32% or 32 times more efficient running on Sierra. So this just shows the power of GPU computing and the next generations of supercomputers, which are going to be highly heterogeneous or to have both CPU and GPU processors. So there's a lot of upside here. To look at verification, these are the PGV maps that result from the 2 calculations. And of course, the underlying code is the same, but the GPU version uses something called Raja as a way to take advantage of the GPU architecture. But we got, to machine precision, the same PGV values and the same seismogram. So that gives us confidence that, we have a verified method. So then we were able, in August, to extend to run a larger calculation. So we ran the same Hayward Fault rupture had a minimum shear wave speed of 500 meters per second, runs for 90 seconds, but this case we used a minimum grid spacing of 9 meters. That required 68 billion grid points, and it ran on 25% of Sierra in about 12 hours or so. And this is a snapshot of the wave field. This is the magnitude of the ground shaking according to sort of a shake map color palette table, and where the reds are really strong shaking. And you can see the very small, the detailed wave fronts here. We're resolving waves that are as short as 70 meters here in this calculation. And this animation is going to show the evolution of the wave field here. And of course, this is within the 3D model of the Bay Area with the surface topography. And there's a lot of geologic heterogeneity. The rupture starts at the star there and moves out, and you can start to, let's see, I wanted to pause that here. Yeah, so at this point, you can see very strong shaking in the East Bay Hills. It turns out there's lower wave speeds in the upper crust in the East Bay Hills due to sedimentary geology that's not present on the east or on the west side of the Hayward Fault. There's only a very thin geotechnical layer that amplifies motions. So we get heterogeneity of the, or variations in the wave speeds across the fault. We've talked about this in some papers that we've written on this, but here, let me just continue this. So you can see actually the wave front races out in front on the west side. It's hitting Richmond right now, this particular wave front, but also has very large motions and delayed in time on the east side of the fault. And then this becomes even more dramatic when the waves start to hit the San Pablo Bay. You can see the wave field is racing out in front at point, north of Point Pinole here. But the amplitudes are much higher on the eastern side of the Hayward Fault in the San Pablo Bay. You can also see the delaying of the wave field and the amplification in the Evergreen Basin out here in San Jose. In this area here, you can see delay and amplification of the wave field right there. See how those wave fronts are curved. You also get some amplification in the San Leandro Basin off here. And then at late times, we have large motions in the San Pablo Bay and going up towards the Sonoma and Napa Valley and out in the San Ramon, Livermore, Pleasanton, Dublin Basin. So that's an animation, and it goes out there for 90 seconds. Here's the peak ground velocity map, or the PGV map, that we get from this calculation, again, resolving waves as short as 70 meters, and you can see very strong red motions almost everywhere. Now let's look at the time histories. This is for a site in Oakland, where we've looked at the resolution, at 0.3 hertz. These are fault normal acceleration time histories resolved to different frequencies: 0.3 hertz, 0.6, 1.25, 2.5, 5, and 6.9. And you can see the amplitudes increase, especially as we get to the higher frequencies. Now, each one of these, most of these are doublings of the frequencies, and each doubling of the frequency requires 16 times more effort. So twice as many points in the X, Y, and Z direction, and twice as many time steps. So the work to calculate these goes as frequency to the fourth. So to go from 1.25 hertz, which is sort of what was typical of a 3D calculation, and it's what's used, say, in the CyberShake method from SCEC, they'll use a maximum frequency of about 1 hertz for the 3D models, and then stochastic random Green's functions at higher frequencies. So to go from 1.25 to 6.9 is about a factor of 1,000 harder computationally. But this is what we get. We get a much richer response that includes the full physics of 3D wave propagation. If we look at a site in the Livermore Valley where we have very long duration, and there's some long wavelength, long period surface waves that are out there that are resolved in the lower frequency calculations, but we see a lot of the earlier time, the rich high frequency energy in the time history there, and of course larger PGA for the higher frequency resolved motions. So now let's look at a site in Oakland. Here are the acceleration, velocity, and displacement time histories in the fault parallel, fault normal, and vertical directions. The displacements, we see the step that you'd expect from a buried dislocation, mostly in the fault parallel direction in the x-axis, which is along the fault. Velocity, we see a strong velocity pulse, in particular, here you can actually see it somewhat in the displacement as well, this step here. And in an acceleration, we're getting up to almost, 0.8 g or something like that, more than 0.5 g peak acceleration. The motions are very impulsive for a site right along the fault. We're basically, seeing their largest when the rupture is passing by. And the duration is not particularly long. There's not a lot of 3D wave propagation effects here because we're so close to the fault that's not really entering into it. And if we look at the response spectra, so the black line shows the Arati 50 response spectra in the full range of the NGA West GMPEs from 100 hertz, 10 hertz, 1 hertz, 0.1 hertz, or 10 seconds, 1 second, 0.1 seconds, or 0.01 seconds. And that's the full range here. We're, of course, resolving to 6.9 hertz, or periods that are greater, shown in the white area. And there's the recorded, or the simulated, from the Rati 50 spectra from the simulation. Also shown are 4 of the NGA West 2 GMPE predictions for this particular site at this distance, magnitude, VS30, Z1.0, Z2.5, et cetera. And those are shown as the colored lines when the 1 sigma errors, which are essentially multiply, divide by a factor of 2. And you can see we're within there, and we're actually capturing the PGA, or the spectral ordinate. That's because, of course, the Earth isn't necessarily propagating 100 hertz energy, but a system that responds to 100 hertz, that has a resonance frequency at 100 hertz, is responding to the motions that are calculated up to frequencies of 6.9 hertz here. And we see a pretty good agreement, though, between across the response spectra. For site out in Livermore here, we have a much more complex path and much more complex response. There's a lot of scattering due to basin effects. A hard rock body of the Diablo Range acts as a wall and reflects energy back into the Livermore Basin. We get a very long duration. Sometimes the strongest motions are late in the seismogram, as you see here in the velocity response. Strong scattered waves and complex. And even after 90 seconds, the motions haven't really calmed down. So we might even need to calculate that longer to capture the full duration. Comparison with the GMPE Rati 50 spectra is shown here. And here we're in the forward directivity. We have somewhat larger long period response. And we also have a complex basin response in these long periods that you see very clearly here in the displacement response. They're not captured by the simple Z1.0, Z2.5 basin factors that are encoded in the GMPEs. So that's an important point, that the 3D wave propagation really adds, complexity that's not captured in the GMPEs currently, I would assert. If we look at, let's see, so across this domain here, shown in the map on the right, we sample the wave field at 2-kilometer intervals. So we have 2,300 sites. And here are the PGA values at all those sites from distances of 100 meters from the fault out to 60 kilometers. Here are the PGA values plotted as a function of the bore distance. And they're color-coded by the Y coordinate, which is essentially the fault normal component or distance. So you can see that the cloud of points here, its mean value is quite consistent with the GMPE predictions. And the GMPE prediction I'm showing is for the Abrahamson Silva Kamai 2014 NGA. The mean value between the computed PGA values and the GMPE prediction is essentially 0, and the standard deviation about that is 0.5 log units. So we have slightly less spread than what's in the GMPEs. If we look at PGV, the mean is 0.17 log units, and the standard deviation is 0.44. So very close to 0 mean or very low bias in these predictions, even close to the fault. And you can see there's a factor of 2 variation in the near fault motions within, almost everywhere. We look at bias. This is now taking every recorded or every simulated motion, dividing by the site-specific prediction with that VS30, that distance, magnitude VS30, Z1.0, Z2.5, and then forming the ratio, the ratio of those two. And then for all 2,300 sites, we then look at the statistics in these box plots. So if we just look focusing here at the period of 1 second, the heavy bar is the median of those 2,000 or so recordings. The box shows the interquartile range. So there are 50% of the data are captured by the light blue boxes. And then the whiskers show 1.5 times the interquartile range. And then the circles show outliers, particular motions that are beyond that 1.5 interquartile range. So we then we form this ratio of the simulated ground motion intensity to the GMPE prediction for that specific site. We then take the natural log of that. So if we had perfect predictions, they would lie on this 0 line here. Of course, they don't. There are variations in there. And you can see, though, the median levels, the solid black lines, are within the plus and multiply divide by 1 sigma variations, which are indicated by the red dashed lines. So this is shown now as we go from the right. We have PGA, then PGV, then the long period, 10 seconds to 5 seconds to 1 second to 0.2 seconds. So from long period to short period, we're plotting those as a function of period. These are the bias plots here. And this is for a 1D model. And the Graves and Pitarka broadband platform, method was calibrated essentially, or was developed, in the broadband platform to give predictions that are consistent with the median values being within the uncertainties, and we get that for the periods above about 0.25 to 10 seconds, and pretty well for PGA, maybe not so good for PG, or all right for PGV, maybe not for PGA. And if we look at the, if we look at the 3D model, there's a lot more variation, but the median values are still within those limits. So this is an important point that, with the median values, on average, the behavior is consistent with the GMPEs, but we have much more variations, and this is due to path and site effects. So what's really interesting is to try to understand why this point is so much higher or this point is so much lower than the GMPE, and can we try to figure that out? Is that repeatable by running these calculations, say, over and over again for different ruptures? When we go now, these two cases were the 1D for 5 hertz and the 3D for 5 hertz. When we look at the 3D case going to 6.9, we then bring these motions up, these shorter periods, and we're doing pretty well even at 10 hertz frequencies, or 0.1 seconds, and we do a better job with PGA. So as we go to higher frequency, we're able to reduce the bias at the high frequencies. All right, this just shows sort of the progression. If we look at the maximum frequency here on the x-axis and the number of grid points, or the total memory required to do the calculation, this point here on the left was done in 2012. This was in 2014. Really, since we started the exascale computing project, we've been working on these. And the solid gray line shows the number of points required for a case with a uniform mesh with a uniform grid spacing. You can drop down to this dashed line by using the Cartesian mesh refinement that has been implemented in SW4, and that reduces for the Bay Area problems about a factor of 6 the number of grid points required. And that's enabled us to march further up and to the right here to resolve higher frequencies. Now on the Sierra machine, we've gotten up to close to 100 billion grid points, and but we could fit larger problems on there, so we're hopeful that we can try to do that. And there are some other improvements we hope to do. Let's just take a look now and think about Moore's law and the IEEE's top 500 list and earthquake safety. So of course, Moore's law is the observation, published by Gordon Moore in 1965, that the number of transistors in an integrated circuit doubles every 2 years. And if we look at the top 500, this is a ranked list of the 500 most powerful computers in the world, published every twice by IEEE. And going from 1995 to present, the current values are up here. This is in the y-axis is in gigaflops, or billion floating point operations per second. So we're up here now with the Summit machine at Oak Ridge, and Sierra's number 2. Then the bottom of that list, the 500th computers here, and that keeps increasing, of course, also. And then this blue line is the sum of all those. But you can see that we just keep moving up and to the right and having more and more powerful computers. If we're doing better than doubling the power of these of the computers, the fastest computer every 2 years. So computers keep getting more and more powerful, and they're enabling radical changes in how we do science and engineering and approaching challenging problems, that impact society. And technology companies now anticipate this growth. They're without really knowing the specifics of the next generation architectures, but they plan on this growth. So there's really a great opportunity for future methods, and seismic hazard and risk could rely on physics-based 3D simulations to provide ground motions for structural response and performance-based design. And I think we're at a really exciting time when we're able to calculate motions that are getting into 5 and higher hertz frequencies on large domains that are able to provide meaningful input for structural response. So I'm interested in how this community sees that and might make use of those types of motions in the future. So I'm going to wrap it up now to summarize. Advances in numerical algorithms and computational efficiency are enabling us to calculate higher frequency ground motions. This curvilinear mesh refinement with topography is key. Topography is key as we go to higher frequencies. It's one thing we know very well about the Earth. Mesh refinement is really key to memory efficiency. Using a hybrid approach to use MPI and OpenMP for many core CPUs is key. But as we get ready for GPU computing and heterogeneous computers that are very intensively, they have a lot of GPUs, that's going to be really allow us to make significant improvements in performance, more grid points and faster runs that enable us to sample, say, a range of rupture models, or to do the inverse problem for the structure in full waveform inversion. Simulated ground motions are realistic. They're consistent with the ground motion models. We haven't really, strictly speaking, done validation, but we could do that if we were to have recordings of a very large earthquake in a region for which we have a decent 3-dimensional Earth model. Let's see. So really, that's going to be one of the challenges, though, is getting a better 3-dimensional Earth model. And of course, these motions are allowing engineering analysis and looking at the effect on structures. So a couple remaining challenges is we need to improve the 3D geologic and seismic model. And to do that, we need to first evaluate the current 3D model with moderate earthquake waveforms. These are the magnitude 4s and such earthquakes that we record, that are recorded by dense networks in the Bay Area. We need to look at the path-specific model performance. What frequencies can we model? What ground motion intensities can we capture? If we're not able to capture, say, wiggle for wiggle, can we look at some intensity measures or spectral measures? And we hope to improve the model with 3D full waveform inversion. And there's an effort within the USGS to try to also talk about, model improvement and development as a community effort. And that would exploit both travel time and amplitude information in the waveforms. Really an important question is, can an improved 3D model predict path and site effects? These are repeatable, right? The path and side effects, the Earth is constant, fortunately. So it should, produce the same physics of wave propagation. So if we were to use a non-ergodic ground motion model, would we be able to really predict path and side effects following what's been done recently by Lin et al. And Landwehr et al. Specifically in Landwehr in California, looking at path effects. And if we could do this, we could probably reduce about half of the uncertainty, right? Half of the uncertainty is within the source and about half is in path and site. And if we could reduce that, that would be a great contribution to be able to reduce the overall uncertainty and limit, be able to have more confidence in our predictions of median behavior. We're also looking at the impact. We assume a certain minimum shear wave speed in our calculations. We've recently submitted a paper on that effect and also on the fault geometry. The Hayward Fault actually is not vertical. It's not a vertical strike slip fault, but it actually dips to the east. And we've looked at that a bit as well. So, and then here's just, if you lived in Berkeley or Oakland, this is the event that woke you up at 3 a.m., 3:30, whenever it was on January 4th. And it was recorded by these stations here. These are stations operated by permanent networks operating in California, and this data is organized over at UC Berkeley. So these data are going to be really valuable for testing our model. Last things I'll say are just some thoughts. As we go to higher frequency, we really need to look at a lot of the effects of various assumptions on our source: the slip, the rupture speed, the rise time, fault roughness. Nonlinear geomechanics is probably important as we get to both near the fault and in site response for these very large motions near the fault. We have to resolve finer structure in the 3D model, both on the crustal scale, but how do we incorporate the near surface geotechnical layer, which could require very fine discretization? How do we incorporate that into the model? Norm has sort of outlined 3 acceptance criteria. We need to be able to provide unbiased prediction of the median ground motions. And I think, we're being able to do that. We haven't done a lot of cases, but the cases we've looked at so far look good. We need to predict consistent variances of the source, path, and side effects, and that remains to be shown, but we need to generate a suite of ground motion calculations for a range of ruptures and then look at that breakdown of that variance. And Norm's work with Jeff Bayless recently has looked at spectral correlation properties, or the interfrequency correlation, and that's an important property that impacts fragility. So those are just some thoughts of things that are on the horizon for us, and both things we need to be cognizant of and future challenges. And I'll stop there, and thanks for your attention.
Thank you, Artie. Thanks for sharing these results. And at this time, we'll move on to a question and answer session. Attendees, you're reminded that questions should be submitted through chat panel and sent to the moderator. Fascinating results, very, very impressive. What you've been working on. So a couple questions came up about the acceleration time histories or the actual results that you've obtained. The first is how does somebody obtain these ground motion results? Are they available to the community? And particularly for those of us who live very close to that star that marks the epicenter for your scenario, really hits home.
Well, let's see. So we have a data product. We published the paper in January in Geophysical Research Letters that looked at us, not quite, I didn't show that one here, but it was a magnitude 7 earthquake. It had slightly different fault geometry. Similar domain, it resolved up to 4.2 hertz. And we have a data product that is the time histories on a 2-kilometer grid. So there's 2,301 sites throughout this domain. that are evenly spaced. And that's essentially would be these time histories that you see in this plot here. And I've made that available. It's been, people looking at earthquake early warning have that data. So if anybody contacts me, I have a problem with a tar file right now that I need to fix, and I'll probably do a tweak to that, but I'm very easy to find on Rogers7 at llnl.gov, or Google my last name, Rogers, like Rogers Creek, and contact me and we can figure out. It's about 100 megabytes. And I can provide data for the 1D model and for the 3D model with topography. And those are about 100 gigabytes. They're SAC files, which are readily convertible into other formats if that's what you want. So I can't provide ground motions at random points or solicited points, but I can have them at those, and that's typically what I've looked at, so that when we look at, ensemble behavior, we're doing it on a nice uniform grid that allows us to really sample, the variations in an unbiased way, which is one thing you can never do in nature unless we put out, 2,000 sensors.
Right. And so another question that you touched on a little bit was the need to validate your simulations with historical events. Could you, so the question was, have you done that? And I think it was answered during the presentation, but maybe can you elaborate a little bit more about what would be needed?
Yeah, right. So we have to be able to reproduce behavior that's encoded in the GMPEs, or ground motion models, for our motions to be acceptable by earthquake engineers, I believe, and seismologists. But that's, a necessary but not a sufficient condition, for true validation. We have, fortunately, there hasn't been a magnitude 7 earthquake, recently with all the recordings on the Hayward Fault. But events like this, these magnitude 4 events, there are hundreds of these in, the archives of the Northern California Earthquake Data Center at UC Berkeley. And, let's look at this a little bit. So there are the red, the magenta is the initial, it's actually a final location, but it's wrong. This event didn't happen underneath the flats in Berkeley. It happened under the Claremont Hotel, or quite near the Claremont Hotel, on the Hayward Fault. And the red star, or the red circle, is the double difference location. So that's a relative location with the whole ensemble of earthquakes along the Hayward Fault. And it's the best, least biased estimate of the location. But I show it just to sort of point out some of the challenges we have. And of course, there's a focal mechanism of this event, both from first motions and from regional moment tensors, that shows it's, as expected, a right lateral strike slip event. We have to put that into, we would then have a domain here that might capture some 50 kilometers around the event. And we would then specify the location and time and magnitude and mechanism of the fault, and then predict, for each one of these triangles represents a seismic station either operated by the Berkeley Seismic Network, in blue, which are broadband stations, which are the most valuable. And they're actually very carefully deployed and very quiet, so they have very high signal to noise. The yellow are the Northern California Seismic Network, operated by the USGS. And these are strong motion stations. Some of them happen to be in people's houses and garages. Some of them are near, infrastructure. Some of them, are permanent stations that have been operating for many, many years. The cyan color is the Advanced National Seismic System, which is run by the USGS. But it's a national program. And you can see it has a bunch of stations operating around. And then lastly, the orange is the California Geologic Survey, California Strong Motion Instrumentation Program. And, so there's very good coverage where people live, you can see, along the East Bay and in San Francisco. Not so good coverage in the East Bay Hills where we see those very large motions. So, it's uneven coverage, obviously. These are strong motion stations which are, meant to characterize motions where they affect infrastructure. But so we have done some tests of these types of events, and we've shown that there are differences across the Hayward Fault. Preliminary indications might be that the differences in the 3D Earth of say the shear wave structure across the fault is not as dramatic as it is in the USGS model. I think if we go down here, this shows the depth to the shear wave speed of 1,000 meters per second. So this is the Bay Area tipped on its side. So north is sort of up and to the left here. You can see there's Point Reyes. Let me show a different map and orientation. This is the depth to the 500 meter per second. There's Point Reyes, there's San Francisco, the bay is here, San Pablo Bay, the delta is up here, and the Central Valley at the top. So the Hayward Fault is along here, and you can see it's characterized by a large change in the material properties. In the East Bay Hills, the wave speeds are 500 meters per second at the surface, but they're much lower, and they're as low as 100 meters per second in the Bay Muds. So, but that is also very thin. So anyhow, we put this in and tried to do some comparisons. There are features in the USGS model that we believe are verified or validated by the moderate earthquake recordings, but there are also key differences, and that's going to have to remain the topic of another discussion.
Okay, and just one final question. Early in the presentation, you showed the domain where we are missing large magnitude events as the basis for this research work, or for your work. And the question is, what locations, for example, other places on the San Andreas or Los Angeles or the Pacific Northwest, East Coast or worldwide, or how many scenarios do you think are needed to fill this gap?
Well, that's a very good question. So if we just think about magnitude 7 on the Hayward Fault for sort of the central segment that would stretch from, say, Richmond to Fremont, we might need to calculate 20 or 30 realizations of different slip models and different hypocenters of that scenario, just to try to sample the possible variability there. And Norm Abrahamson has estimated that. I think it has to do with just median counting statistics, but that would be a first target. I mean, we've done essentially 2 simulations. We did the GRL paper, and then we did a most recently one, the one I described, slightly different fault segment and different slip model. We do see some consistent behaviors between those in terms of path and site effects, which is encouraging, but we need to go well beyond just 2 realizations, and maybe, say, for magnitude 7 on the Hayward Fault, we might want to look at 20 or 30. And then, what's great there is at a given point, we'll have 30 realizations of 30 time histories, and we can actually start to do some real statistics and ask, okay, what is our median prediction? And we'd have a relatively unbiased prediction of the median with 30 values. And now what is the spread? And then how can we break that down in terms of the contributions of the variability due to source, path, and site by looking at variations in median and spread behavior between sites. So I think that's a future direction of this work. And, we'll be trying to pursue something like that. And then one of the challenges here, though, with this particular map, and of course here, there's a cover of earthquake spectra, I think, with a picture just like this. we don't have, for a large, strike slip event, I'm not sure. I mean, a lot of these, there are a lot of motions from Chi-Chi and Northridge and Tohoku, which aren't really the, strike slip continental, crustal strike slip that we need. So that's a challenge. So hopefully that answers your question.
Yeah, thank you very much. We are at the end of today's SimCenter webinar. On behalf of the attendees, thank you, Dr. Rogers, for taking the time to share these results and answer our questions. To the attendees, thank you for your questions. I encourage you to register for future webinars and other upcoming NEARI events that you can find advertised on the designsafe-ci.org website or distributed through email announcements. You can also join our Slack community to continue discussions such as this on topics in natural hazards engineering. Please check the SimCenter's website, simcenter.designsafe-ci.org, and check your inbox for emails from announce@designsafe. Thank you for attending today's Advances in Computational Modeling and Simulation webinar.